Thanks for watching my video today. Let's try to evaluate or let's expand this 1 plus x to the power n where n is greater than or equal to 0. So which means this is a binomial theorem. Okay. Now in the earliest we have proved that binomial theorem then is x plus a to the power n, which is n combination 0, x to the n plus n combination 1, x to the n minus 1, a plus n combination 2, x to the n minus 2a square plus and so on plus n combination r, x to the n minus r, ar plus and so on plus n combination n, a to the n. So this is the binomial theorem. Okay. Now using this we are going to prove the expansion of 1 plus x to the power n. Here put a equal to x. Okay. In place of a, let's put x and x equal to 1. Right. Now 1 plus x to the power n, using that n combination 0, x is 1, right? 1 to the n plus n combination 1, x is 1, 1 to the n minus 1, a is x, right? Plus n combination 2, x is 1, so 1 to the n minus 2, a is x, which is x square, plus and so on. Plus n combination r, 1 to the n minus r, x to the r, plus and so on plus n combination n, x to the n. Now 1 plus x to the n is, so 1 to the n is just 1, right? N combination 0 plus n combination 1, 1 to the any power is just 1, so n combination 1 x plus n combination 2 x square plus and so on plus n combination r, x to the r plus so on plus n combination n, x to the n. Now let's use, so this is actually this is the expansion of 1 plus x to the power n, right? In terms of this combination. But if you want to expand more, now using the combination formula, n combination r is n factorial by n minus r factorial r into r factorial, right? So n c0, in place of r let's put 0, which is n factorial by n minus 0 factorial into 0 factorial, which is n factorial by n minus 0 is n, so n factorial 0 factorial is just 1, so which is equal to cancel out just 1, right? And n combination 1 is n combination 1 n minus 1 factorial into 1 factorial, which is, so n factorial can be written as the decreasing one, right? It decreases. Factorial means it decreases. So n factorial, so in place of n factorial, n minus 1 factorial upon n minus 1 factorial into 1 factorial is just 1. Why we expand this? Because in the denominator there is n minus 1 factorial, right? So we can cancel out these two. So we are left with just n. Now n combination 2 is n factorial by n minus 2 factorial, 2 factorial into 2 factorial, which is n factorial is n minus 1 up to n minus 2 factorial, which upon n minus 2 factorial into 2 factorial, right? Now these two cancel out, so we are left with n minus 1 into n upon 2 factorial. So if you keep on going out and so on up to n combination n, right? The last one, n combination n, will be n factorial by n minus 1 factorial into n factorial, which is n factorial by n minus n is 0 factorial by n factorial. So n factorial cancel. So 0 factorial is just 1, right? So n combination n is just 1. Now putting here, substituting the value of combination. So 1 plus x to the n is equal to n combination 0 is just 1 plus n combination 1 is n, right? N into x plus n combination 2 is n minus 1 by 2 factorial into x square, right? Plus if you expand for n combination 3, n minus 1 n minus 2 upon 3 factorial into, this will be x cube. Okay, this will be x cube plus and so on plus n combination, this n combination r is n factorial by n minus r factorial into r factorial x to the r plus and so on plus n combination n is just 1, right? So which is x to the n. So this is also another expansion of 1 plus x to the power n. This and these are same thing only. Okay, so then this is the proof for the expansion of 1 plus x to the n, right?